In the previous in-class problem, we applied the triple product rule in order to develop a relationship of du dv at constant t in order to relate that to pressure, volume, and temperature. In this problem, we're actually going to apply, the steps we took for the calculus of thermodynamics into analyzing an actual chemical process. And so in this problem, what we're going to look at is a classic piston cylinder device. We have 5 moles of a gas that's in the piston cylinder device. And initially, this gas has a temperature of 300 K and a volume of 100 liters. This gas is then compressed to a final volume of 15 liters. And what the problem is asking us to solve for is it's asking us to solve for how much work is required to do the compression, and also how much heat is added or removed in order to do this compression as well. And I'll also note that this compression is done isothermally. Now for this problem, it wants us to do this analysis for 3 different situations. It first wants us to do it for an ideal gas. It then wants us to do it for a gas that follows the van der Waals equation of state, specifically nitrogen, in which the attraction parameter A has a value of 1.4 liters squared bar per mole squared, and the molecule volume parameter B has a value of 0.038 liters per mole. And then in part C, it wants us to then redo the calculation using the van der Waals equation of state, but this time for carbon dioxide, where A is a different value and B is also a different value as well. Okay? So based on this information, what I want you to do here is I want you to pause the video and I want you to draw a schematic of the system. Based on the text in this problem statement, we could draw a schematic of a piston cylinder device that looks like this. And so our basis is 5 moles of gas, whatever that gas may be. In the initial state, the gas has a volume of 100 liters and a temperature of 300 K. And essentially what we do is we compress the system. And in order to keep it, we compress it isothermally. And we know, based on our previous piston cylinder problems, that if we compress something isothermally, in order to keep the system isothermally, we need to release heat from the system as well. Okay? All right, and so after this isothermal compression, our gas will then be in a lower state, in a more compressed state, where the volume is only 15 liters, but the temperature stays at 300 Kelvin. Okay? All right, and so essentially what this problem wants us to figure out is it wants us to figure out what are the values of work and also the heat that are released. And so we have 2 unknowns. And so we need to apply 2 equations to solve these unknowns. For our analysis, we're going to make a couple of assumptions. Right? We're going to assume that this compression is isothermal. And what we're also going to do is we're going to assume the compression is reversible as well. Okay? It's going to be reversible. That tells us that there's not going to be any entropy generated. But more importantly, for the context of this problem, this tells us that the state of our gas, the pressure, its volume, or its temperature, that we could describe the state of the gas using what we call an equation of state. Okay, so something like the ideal gas law or van der Waals gas. Okay. The other assumption we'll also make is something we make all the time. We'll just ignore any changes in kinetic and potential energy. All right. And so now that we made our assumptions, let's start applying our balances. So for the material balance, it's fairly straightforward. No reaction. And it's a closed system, no input-output. So that tells us that the initial amount of moles is equal to the final amount of moles, which we'll just call N, and that value is 5 moles. For the energy balance, we have a closed system, and what we care about are both the initial and the final states. So we'll use the closed difference form of the energy balance. Don't care about changes in kinetic or potential energy. Alright, and previously, when we handled this sort of problem, when we handled an isothermal system, we always made the assumption that because it was isothermal, that the change in internal energy would be equal to 0. Right? But in order to make that assumption, what you have to assume is that you have an ideal gas. Right? What we're going to do now is we're not going to make that assumption immediately. So we're going to keep the du term around. Okay? Alright, so if we do that, our energy balance simplifies to du plus dq plus dw. And if we integrate that, what we get is that delta u, which is equal to u2 minus u1, is equal to q plus w. Okay? And also, in fact, what I'll do here is, here we had the extensive versions of internal energy. But what I'll do is I'll pull out the moles so that we could write the molar versions of internal energy. Okay? Alright, and so far, our two unknowns that we want to solve for are q and w. So this equation, we have two unknowns for one equation, so we can't solve for everything yet. But we do know for work, since we just have mechanical work going on in the system, we could calculate that using the definition of work. And if we apply a force balance on the system, we see that work is going to be related to the pressure of the gas and the integral of it with respect to volume from volume 1 to volume 2. Okay? And so this would be a second equation that we use in order to solve for everything in our energy balance. Alright, and so we've seen this type of problem before. This is, at least the premise of the problem is not anything new. And so when we handled this problem before, we essentially just applied this strategy. Okay? Where the way we would solve it is we would solve equation 2 in order to get our work term, and then we would calculate u2 minus u1 using some sort of equation of state or something. And then once we had those values, we would just then use equation 1 to get the heat. Okay? So that's the basic strategy that we'd taken before. But what I want to focus on now is I want to focus on the second step. So let's focus on this step. Okay? Alright, and so for cases when we were dealing with an ideal gas, we just assumed that our delta molar internal energy, so u2 minus u1, we just assumed that that was 0 for an isothermal process. Okay? So we just made that assumption, crossed out u2, u1, and then that made solving for q very easy. Alright, but once again, that was just an assumption. And what we want to do now is we want to justify that assumption. Why are we able to just say that if we have an ideal gas, the internal energy difference is 0 if it's kept isothermal? Okay? And so what we're going to do is we're going to take a more rigorous approach to proving this. And to do this, we're going to apply the calculus of thermodynamics. Via thermocalc.